Most AI models today generate text one token at a time, slowly predicting each next word based on the one before it. It's how tools like ChatGPT or coding assistants usually work, and while it sounds smart, it actually creates a serious speed limit. This step-by-step process drags down performance in everything from writing code to handling real-time tasks. But now there's a new model called Mercury that breaks that rule completely. Instead of guessing one token at a time, it generates many at once using a method called diffusion, something that's never been done at this scale for language, and the results are shocking. It's not just faster, it's on a completely different level. Inception Labs looked at that bottleneck and said, well, why not jump tracks entirely instead of guessing tokens one after another? Their new model family called Mercury uses diffusion, the same broad idea that has made image generators so good. With diffusion, you start from random noise and tidy it up step by step. But here those steps happen across every position in the sentence at once, because a modern GPU can crunch loads of matrix math in one go. Mercury ends up blasting out code far faster than the older approach, the smallest public version. Mercury Coder Mini has been timed at 19 tokens each second on an NVIDIA H100 card, and the slightly larger Mercury Coder Small still churns 737 tokens per second while adding a bit more brain power. Those speed readings come from Artificial Analysis, an independent firm that times models under the same rules, so it's not just marketing fluff. Speed isn't the whole story. Of course, a coding assistant that misplaces a bracket isn't helpful. So the Mercury crew measured quality on the usual scoreboards on Human Eval, which asks the model to pass hidden Python tests. Coder Small reaches 90% and Coder Mini lands at 88%, MVP. Another Python test set shows 76% for Small and 77% for Mini. Eval Plus, which repeats those tasks with stricter hidden checks, keeps Small at 80%. Then there's Multiple, which spreads questions across C++, Java, JavaScript, PHP, Bash, and TypeScript. There, Small averages 76.2%, while Mini averages 74.1%. In short, the larger Small model sits right with Frontier speed-tuned offerings like Claude 3.5, Haiku, and Gemini 2.0 Flash. While staying 3 to 10 times faster, the smaller Mini model gives up only a few accuracy points, yet still outruns almost everything else in sight. The magic happens because diffusion lets the model polish the whole answer together. Traditional models build answers from left to right, one word at a time, like typing a sentence, and never being allowed to go back and fix anything. But diffusion flips that idea. It works more like editing a shared Google Doc, where you can tweak any part of the answer at any time, even go back and rewrite the start after you've written the end. That's especially useful for coding, where something you add at the bottom might change what needs to happen at the top. And because each pass updates the whole thing at once, it runs way faster on modern graphics cards, which are built to handle tons of calculations all at once. During training, Inception Labs took trillions of tokens, no exaggeration, in a blend of web crawl synthetic examples and proprietary repositories. They add controlled noise, then teach the transformer to de-noisize, step by step, weighting easy and hard steps differently. So the model first sketches broad structure, then perfects details like indentation and naming, because the backbone is still a normal transformer. All the genie bottle tricks developed for standard language models, flash attention kernels, half-precision math, key value caching, fit right in. The heavy lift went into redesigning the sampling loop rather than the neural network layers themselves. Serving a diffusion model, well, is its own art. And here Inception Labs built a custom inference engine. The engine decides on the fly how many denoises passes a prompt really needs, and batches multiple users, so the GPU never sits idle. Simple prompts might finish in 8 quick passes and come back in 25 milliseconds. Bigger prompts can run the full schedule, yet still pump hundreds of tokens each second. From a developer seat, nothing exotic changes. The public API speaks the familiar OpenAI JSON dialect, which means a swap is basically changing one base URL in your client code context. Window length matters when you paste entire files into a prompt. Mercury ships with 32,768 tokens of context out of the box, and can stretch to 128,000 with an extension trick that's long enough to drop in a whole Kubernetes manifest, plus notes, and still have room for instructions alignment and instruction tuning. Follow the same recipes you've heard: reinforcement learning from human feedback, direct preference optimization, but the loss function becomes a diffusion. Denoising loss instead of the standard next token. Loss. Early testers report that chain of thought prompting, few shot, zero shot, all still work. Which makes sense because the conditioning interface remains unchanged. To see how humans react, look at Copilot Arena, a blind taste test site. Developers there choose between code snippets without knowing which model wrote them. Mercury Coder Mini tied for second in overall ELO score, yet delivered the lowest average latency, just a quarter of a second. GPT-40 Mini Codestrol and Gemini Flash needed several times longer to draw their first characters. Reviewers noticed Mercury's answers felt concise, no surplus verbosity. Perhaps because global passes discourage token fluff, it's worth stacking Mercury against the usual top performers. GPT-40 Mini reaches similar accuracy, but tops out at just 59 tokens per second. Claude 3. 5 Haiku sits around 61, and even Gemini 2.0 Flashlight with its high-speed mode barely touches 200. Meanwhile, Mercury, prettily pushing over 1,100 tokens per second, still outperforms them on the speed-to-quality curve as shown by artificial analysis. Even the heavyweights like GPT-40 Full and DeepSeek version 3 struggle to break past 100, consistently making Mercury's numbers feel almost unreal in comparison. A fair question pops up: isn't Diffusion famous for needing dozens, even hundreds of iterations when generating images? That's true in pixel space. But text diffusion can cut steps sharply because the denoiser proposes big edits early in practice. Mercury often takes between 10 and 30 passes. Added together, those passes still spend less time than one auto-regressive rollout because every pass covers the entire sequence at once. Another common worry is resource use. The 19 tokens per second headline comes from an H100 with hand-tuned kernels. You won't hit that figure on a desktop 3090 using plain PyTorch today. Inception Labs fuses operations in custom CUDA kernels, manages memory to avoid unnecessary transfers and schedules. Batches centrally. Whether those improvements trickle down to open source remains to be seen. But history suggests community ports follow soon after commercial debuts once people see the gains. There's a green angle too, if one GPU serves 10 times as many tokens in the same time slot. Cloud providers need fewer racks and smaller organizations can stay on smaller clusters. That lowers the bill and the carbon footprint as more devices move inference to the edge. Think office laptops or on-premise servers. These savings become practical, not just theoretical. The Mercury report even hints that Diffusion's efficiency could open room for multimodal expansion, pairing text with diagrams, audio descriptions, or even quick video scrubbing using one architectural family instead of stitching separate specialist models. The paper also covers scaling laws. Their larger small model beats Mini by a clean margin on every benchmark, implying performance should keep rising as they release medium, large, or beyond, because each denoises pass is still one forward transformer. Run bigger layers could mean both a richer model and even more parallel work per pass. So speed might climb rather than fall up to bandwidth limits. One spot where Mercury still trails is Bash. Scripting 50% accuracy for Coda, small versus Gemini Flash's 51%. That shows there's room to train on more shell samples, yet in JavaScript, TypeScript, and C++, the diffusion model already matches or edges past most rivals, and its fill-in-the-middle scores 93%. For single-line gaps in small top the charts, those fill-in-the-middle tasks matter, because real coding assistants often work by dropping hints exactly where you're typing, not at the end of the buffer if you want hands-on proof. Inception Labs runs a free playground at chat. Inception. AI paste up to 128,000 tokens if you're brave. Watch the spinner and notice how little delay there is before full paragraphs appear. They do throttle heavy users, but it's enough to feel what sub-100 millisecond code completion can look like. Behind the curtain, the training cluster clearly burned serious compute. They didn't publish the exact GPU count, only that everything ran on H100s, and that the data pile reached trillions of tokens, still because the same denoiser weights apply across all time steps, fine-tuning floating point operations per sample, compared to normal language model fine-tuning. That opens the door for smaller companies to specialize Mercury on private code bases without astronomical cloud bills. The bigger picture is that Diffusion just stepped out of the image world and into the programmer's chair. It isn't tossing out transformers, it's reusing them in a fresh sampling loop that finally breaks that left-to-right handcuff if you build developer tools or maintain giant internal code assist systems. The arrival of 700+ tokens per second at solid accuracy changes capacity planning overnight. Alright, that's it for now. If diffusion models are already this fast and accurate, what's stopping big players like OpenAI and Google from switching everything to this approach? Or are they just protecting what they've already built? Let me know what you think in the comments. Don't forget to like, subscribe, and turn on notifications. Thanks for watching and catch you in the next one.